Good afternoon, it's Rachel from E1. We'll begin broadcasting in just a minute to allow all of our participants to join in. So please just give us a few seconds, thanks. Hi everyone, and welcome to today's live session of Evaluating Sewer Alternatives. We're covering the last in our three-part series for the next hour, and we'll be focused on an overview of life cycle cost analysis. I'm Rachel Seiler, today's host and Marketing Communications Manager for E1. As always, before we get started, I have some housekeeping notes. Attendee lines have been muted. We'll be recording today's session, and an archived edition will be available on E1's website and YouTube channel. Upon successful completion of today's webinar, you'll receive a PDF of the presentation, a link to download our life cycle cost calculator, as well as a certificate of attendance. And finally, we'd love to hear from you. We've allotted about 10 minutes or so of Q&A during today's session, so please make use of this time. Keith loves answering questions. If we don't get to all your questions, we'll answer them in a follow-up email. So now, without further delay, I'd like to introduce today's speakers. Both are seasoned E1 presenters, and if you've attended any of our previous webinars, you may recognize their voices. We've got Chris Nedwick with us today. Chris is E1's National Sales Development Manager. With more than 10 years of experience in both E1 sales and field service, Chris has guided many municipalities through successful pressure sewer projects. A nice welcome to Chris. And today's featured presenter is Keith McHale, E1's Applications Engineering Project Manager. Keith is a professional engineer licensed in Maryland, Virginia, Connecticut, and New Hampshire, with 30 years in manufacturing and consulting engineering, focused in wastewater collection and treatment. As a consulting engineer, Keith's projects involved evaluation, planning, and design of wastewater collection systems and treatment and disposal facilities. So Keith, this means you're up. Take it away.
Thank you very much, Rachel. And thank you all for attending our third part webinar, or the third part of our three-part webinar series. Today, as Rachel mentioned, the topic is the overview of life cycle cost analysis, looking at the final process that we would go through. For those of us, hopefully most of you, if not all of you, have been with us for the first two parts. And really what the agenda here was kind of to present an overview, if you will, a process of evaluating sewer alternatives. So we started off in part one with an overview of wastewater collection systems, looking at the equipment and the operation and maintenance and just basically how the system works, focusing primarily on gravity sewer and low pressure sewer systems. Then in part two, we moved the evaluation process along, where we started to look at the basic system design principles. So at this point, we eliminated all other alternatives and we focused strictly on gravity and low pressure sewer systems, and just looked at some of the design principles, some of the considerations that you would do as you make the project evaluation process move forward, really looking to see which of the sewer alternatives we shortlisted are technically feasible. So then once you establish, what the systems are, which ones are technically feasible and how do they work, then we'll move into the third process of evaluating sewer alternatives, and that is looking at kind of the overall life cycle cost analysis. And when we look at the life cycle cost analysis, we're looking at a couple things, really focusing on the non-technical aspects. So in part one and part two of the webinar, and as you're working through that process of evaluating sewer alternatives, you're evaluating the technical feasibility of the systems. So let's say at this point, we now have established that both gravity sewer and low pressure sewer systems are technically viable to service our community. Now we'll start to look at the next layer of analysis, and that's looking at one we term the triple bottom line. And that's looking at the social, the environmental, and the economic cost associated with the project. So just because it's feasible from a technical standpoint doesn't mean it's the best solution. So you want to look at this triple bottom line approach as well. And then as part of the economic cost of the triple bottom line, we would look at a structured life cycle cost analysis. Because it's important when you're doing the evaluation to consider all costs associated with the project, not just the initial capital cost. You want to see how is that initial capital cost structured over the project. Is it all up front, or can it be spread out over phases? And you also want to make sure we capture any ongoing costs. You know, one of the problems the industry ran into, or was a problem within the industry, particularly during the Clean Water Fund grant loans, where money was basically free. It was easy to build a system, and then many operators and utilities found out that they didn't necessarily budget for the cost to maintain that. So when you're doing the evaluation, it's important to look at all aspects of the economic cost. Quick recap on where we've been. I do believe this is the same slide that was in all three parts. So those of you that have been with us throughout have seen it. But we're looking at two types of systems. We've got our conventional gravity sewer system that is designed to take advantage of the force of gravity as the prime driver for wastewater flow. The wastewater leaves the house and then flows downhill in the gravity pipe to a lower point. The design and installation is dependent on maintaining that constant downward slope so that you're able to maintain minimum acceptable flow velocities to keep the wastewater solids suspended and so they don't clog up the pipe. It becomes a concern when you start to flow downhill and the excavation to install the pipe becomes deeper. Then it gets either difficult, if not impossible, to dig a deeper trench, or if you can do it, it becomes very expensive. And not only is the expense of digging a deep excavation for gravity sewer a concern, the health and safety aspects of that is something to consider as well. So when you have the conventional gravity sewer, you're going to dig that downward sloping pipe to the point where it's no longer feasible to do so, in which case you would install a lift station that would then lift the wastewater up to a higher hydraulic elevation, and then it can continue either that downward flow by connecting to a trunk sewer, or perhaps it's just a force main that goes directly to the wastewater treatment plant. For pressure sewer systems, it's pretty much a lot different. We have a individual grinder pump that is located at each property that grinds up the wastewater and then discharges it into a small diameter pipe in the roadway or adjacent to the roadway that is buried just below the frost line. The prime driver in a pressure sewer system is the pump. So you don't have any concern with having to install that pipe on a downward slope. The pump moves the wastewater through the system. In fact, the pumps do. You have many pumps throughout the system. So the grinder macerates the solids into small particles, and then the entire wastewater and solids flow either to a central treatment system, or it could be part of an existing larger gravity sewer system. So you might have a 100% pressure sewer system that discharges to a treatment plant, or you might have a pressure sewer system that discharges to a lift station or a gravity sewer system. Usually if it's going into a gravity sewer system, it would be either at the lift station or at a gravity sewer manhole. Pretty simple process. Every manufacturer is going to have something that looks very similar to this, where you have the basin that is located on each property. Within the basin, you have the pumps. And depending on the manufacturer, everything else could be part of that pump. In the case of an E1 system, we have the E1 core, where you have the float controls are part of the pump, or the float sensors that tell the pump to turn on and off are part of the core, as well as the controls itself. So everything is part of that core, and then it sits in a nice little funnel. With the centrifugal grinder pump, those components will be separate from the core and be taking up some of the space within the basin. And with the centrifugal pump, you would tend to have a typical guide rail system where the pumps come out by lifting up through the guide rail. But the principles are the same. The wastewater flows from the house to a standard 4-inch, or depending on local codes, maybe it's a 6-inch service lateral, flows by gravity to the basin. Once the water level in the basin gets to the predetermined level, the grinder pump turns on, grinds up the wastewater, and then discharges it into a small diameter service lateral. And that small diameter lateral would typically be about 1¼ inches or 30 millimeters, and then discharge into the mainline sewer. And again, this is a flexible pipe installed just below the frost line. Typically, it's going to be a 4-inch pipe. On some very large systems, you might see a 6-inch or 8-inch diameter pipe. But generally, we found doing an evaluation that looking at a whole lot of large data collection of pressure sewer systems, I think it was like 94% of all pipe was 4-inch diameters or less. With a gravity sewer system, you have an 8-inch diameter pipe that is going to be buried a little bit deeper to begin with, and then continue to get deeper. And that distinction is really critical when we start to get to the latter part of the presentation and look at the cost, and we look at some of the drivers that influence what the cost of a system is. So it comes in, grinds it up, and then discharges through the small diameter pressure main. So as we get to this point, we've kind of gone through our evaluation. We determined at this stage that gravity sewer systems and pressure sewer systems are technically viable. So we want to start the selection process. And there's a couple ways you can do this. I've always been a big fan of kind of a matrix system. And when you're looking at it, there's two sides that you really want to focus on. I think this goes, true of any decision-making process. You get the objective analysis and the subjective analysis. The objective analysis are things that everyone pretty much would agree on, and you're not going to have a lot of subjectivity to it. And that'd be, the technical performance criteria. Does it meet the technical requirements? Can it convey wastewater from the household to the treatment plant? Then you want to look at the economic criteria. That again is very objective. You're not going to have much, if you ask 5 people what it costs, you might get a little bit different opinions, but it's not really subjective. It is a more or less objective, non-variable type assessment. The other side of that, though, is the subjective analysis. And this is things where, many different people will have many different opinions on which is the better alternative. When we look at the subjective analysis, we're looking at some of the non-monetary criteria. One, is it suitable for the collection basin? Technically, it's acceptable, but that doesn't necessarily mean it's suitable. There are other considerations when we look at suitability, and some of that would be, as we get further into it, maybe the triple bottom line when we're looking at the social cost. Tearing up a street is not suitable in most applications. Ease of operation and maintenance. After this thing is in the ground, someone's got to maintain it. So that comes into evaluation, and everyone's going to have a different idea of what is ease of operation and maintenance. Operational familiarity. Is the operator familiar with it? That's something that has to be considered. Community impact and environmental impact. And again, these are part of the triple bottom line where it may or may not be a critical component of the decision-making process. Many people may have different opinions on the value of it or even what the criteria should be for it. But it's something that you want to consider just to say, yeah, we looked at this and from a community standpoint, it is, or maybe it is not okay. And you got to remember which way to go. I'm a big fan of kind of the matrix analysis system where you go through and you rank things. So this is just kind of graphical. Normally I might have a number in there or some sort of scale. And here, in this example, we're looking at a lower horizontal bar is a less favorable alternative versus a more favorable being the longer horizontal bar. So you would go through when you look at your evaluation criteria, breaking it down from the monetary to the non-monetary, and assign a value to the parameters that you set. And those parameters, here I got the monetary, the capital, and the O&M. That's pretty standard. But once you get down to the non-monetary, the subjective analysis, that's really going to vary a lot. You may have a lot more criteria that you want to consider than I'm showing here. It's really going to be a lot of user preference or more importantly, client preference and community preference. So you know, it's a good process to go through and, like I say, assign a numerical value or thumbs up, thumbs down, something just so you can look at graphically and say, okay, based on this evaluation, here's how we should move forward, or here's the recommended move forward. So we're going to move to the bottom part of this graph first, focusing on the non-monetary. A big part of that is when we get into the triple bottom line. The triple bottom line is three components of what would be perceived as the cost. Now, y'all don't have the benefit of seeing me do air quotes when I say cost, but you know, two of those don't have a real cost, but we kind of consider it a cost because in many cases it's a cost to the community, it's a cost to society, it's a cost to the environment, as well as an economic cost. And the triple bottom line consists of the three components. We have the economic cost, which is our economic capital cost, the operation and maintenance cost to run the system. Those combined give us a life cycle cost. And then my fourth bullet on the economic triple bottom line component is that gravity is not free. You know, one of the things that is important to consider when you look at systems, you want to make sure you look at everything. And I put that in there specifically because so many times I've had conversations with people and they'll say, yeah, we know gravity has its limitations and it's more expensive than a pressure sewer system. But once it's in, we don't have to worry about it. And that's not the case. So you want to make sure you capture all those economic costs. And we're definitely going to go into a little bit more detail with that as we get into the presentation. And then the other two components of the triple bottom line is the social cost and the environmental cost. So the environmental cost, you know, that's one of the ones that may or may not be a factor where you are, depending on where you are. And the environmental cost can include many things. You know, certainly on one level, it can be the carbon footprint. It could also just be the environmental disturbance. So we want to look at that. And then the social cost, that's, again, not an economic cost that no one's paying the bill on that, but that's the cost to society, the disruption to the community when you're tearing up the street. So we want to kind of go through and really look at this. So today, I'm really going to do a top level look at the environmental cost and the social cost, just sort of to introduce the concepts. These parameters, these evaluations would vary depending on where we are regionally or client-wise. Some clients may put more value in the environmental cost than other clients. Some regulators may require that greenhouse gas emissions be considered. So the environmental cost, as I said, it's the overall cost of the environment. It's always a little bit hard to quantify, so you have to kind of establish what you're trying to look at in the beginning. But we see that there is a lot more attention being paid to greenhouse gas emissions and the carbon footprint. It's very difficult to quantify what the carbon footprint is for a wastewater collection system, but there is some ways to do it. So that might be something that is a consideration. The other environmental costs, though, are the ones we would see more often. And those would be the disturbance or the disruption to the environment that you see directly. Certainly not to discount any mountain icebergs, but the greenhouse gas emissions isn't something we see tomorrow, but digging up a wetlands to put in a gravity sewer system is something we will see immediately. So we want to look at those environmental costs of disturbance to the environment. And again, that'd be wetlands, or might even be just having to clear cut a lot of trees, because with the example of a gravity sewer system, you have to go in a straight line. There's no ability to deviate. That might involve taking out trees or other environmentally sensitive areas. So as you're going through them, you lay out, you remember from the second part of the webinar series where we talked about laying out a gravity sewer, laying out a pressure sewer system, how it's done. Is the best place to lay out that sewer? Would it require the removal of trees, bushes, and landscaping? I don't know that there's any real magic when we look at the environmental cost of a pressure sewer system itself. It's certainly not any detriment from a greenhouse gas carbon footprint emission, but where we see the advantage is the construction means and methods of pressure sewer systems. Recalling from the previous two parts, pressure sewer systems can be installed using horizontal directional drilling or low impact cut and cover. So these construction means and methods will typically yield a much lower greenhouse gas emissions and carbon footprint. So this table I'm showing is from a report comparing the cost of trenchless versus traditional methods of construction. And this report was not necessarily focused on wastewater collection systems. This was done by an industry that was just looking at utility installation. So they considered everything, gas mains, water mains, sewers, anything that was a pipe going in the ground, underground, horizontal assets underground. And they found in this evaluation that trenchless construction methods can result in an 80 to 97% lower greenhouse gas emissions compared to open cut excavation methods. So again, there's nothing necessarily about the smaller pipe diameter and the grinder pump located at each property, but the ability to install a low pressure sewer system with low impact cut and cover or horizontal directional drilling methods can have a definitely a positive environmental impact. In addition, you know, as I said, you get your operation and maintenance cost, but you can also look at your energy and your greenhouse gas costs. And that is something that is really hard to quantify when you want to look at a carbon footprint for a wastewater collection system. The challenge that I've always had, you know, in my consultant days when we would look at carbon footprints is, where do you start? You know, do you start with the equipment manufacturing process? Do you take into consideration what it takes to build or to manufacture that pipe that's going in the ground? And there's not a lot of evaluations on there, but I did find this one report done in 2000. This was presented at a WEFTEC presentation in about 2000, where they did look at the energy and carbon emission for gravity sewer and pressure sewer systems, and looking at the total life cycle cost, basically the cradle to grave evaluation of what is the energy cost associated with manufacturing the pipe, transporting the pipe to the site, installing the pipe, running the system, and then bringing it to the treatment plant. I also believe they looked at the disposal process. So it was a very comprehensive evaluation, the only one I've ever seen. But here we can see that when we look at pressure sewer versus gravity sewer, and we look at the life cycle energy and the life cycle carbon emissions, there is a significant percent reduction of about 50% of the pressure sewer advantage over gravity sewer system. So that's where we see a lot of the environmental costs. And again, one that I don't have a table for is taking out a tree, avoiding wetlands. Then we look at the social cost. Social costs are those indirect costs associated with work that is paid. There's the quotes. You couldn't see it when I did it, but you can see them on the slide. Paid for by the community. As a young engineer, when I was doing construction inspections, that was when I learned about social cost. The contractor's installing the pipe. I'm the construction inspector standing there making sure everything goes according to the plans and specs. Not much more than that. That's an indication to the homeowners to say, hey, that's the guy I want to go yell at and find out when they're going to be done digging up the street. I have to go 4 blocks out of my way just to get down to the store. That's the cost that society pays. It's the business losses, the diminished quality of life, the traffic disruptions, noise pollution, depending on where you are. You know, if you're digging a very deep gravity trench in the middle of the summer, in some parts, it's going to be dusty, it's going to be dirty. If it's not dry and it's very wet, it's not going to, that dirt is going to be mud. And that can create a lot of headaches within the community. Also, it's a big concern with worker safety. So there's not a, there's a cost associated with worker safety in terms of spending it. But the big thing is it doesn't matter what safety plan you have in place. If something goes wrong, that is a bad social check that's being written by somebody. And then in addition to that, damage to paved surface areas, utilities, and adjacent structures. So when you do the evaluation, you decide that we're going to go with this way. Say, well, what are the impacts? Not looking at just the technical feasibility and the economic feasibility, but what are the impacts to the community? The social costs will vary depending on where you are, and they're also going to be unique to every project. And when we look at the social cost, again, it's not that there's anything magical about a pressure sewer system, but it comes down to the construction means and methods. That with the pressure sewer systems, you have a smaller pipe buried just below the frost line that can deviate horizontally and vertically. You don't have to run a straight pipe going downhill at a constant slope that you do with the gravity sewer system. So you have a lot of flexibility. You have the horizontal directional drilling or the low impact cut and cover. So this means we're going to have less damage. Also, the contractor is able to install more pipe in a shorter time period. So the productivity of the sewer installation is quicker. That means the contractor's crews are going to be on site for a shorter period of time. So they're going to be not taking up all the good parking spaces. So you got less construction time and disruption. Also, there's a potential for less impact to existing utilities. With a gravity sewer system, it will always be the lowest utility in a utility corridor. With the pressure sewer system, you got to make sure that you maintain the required separation between water and sewer, but you have a lot of flexibility in getting around other obstacles. So it doesn't always have to be the lowest utility, or if it does have to work around other utilities, it's easier to deviate that pipe, that small diameter pipe, horizontally and vertically. And I always like, to illustrate it through pictures. This slide shows what I would consider high social cost with traditional cut and cover associated with gravity sewer systems. You got large equipment in the middle of the road, installing pipe at a slow pace, construction workers in the trench. I always do make a point that I try to have a trench box and hard hats on these pictures, but those of us in the industry know that you don't always have OSHA approved methods going on. I talked back, like I mentioned earlier, when I was a construction inspector. Back when I was a construction inspector, we were actually called inspectors. Now I believe the term is construction observer, because you don't want to tell the contractor something unless it's a definite health and safety risk. But you want to make sure that you're not tearing up the street, that you're not disrupting the community. Compare that with a pressure sewer system where you have that construction means and methods. So we have that low impact cut and cover, that horizontal directional drilling. So with the pressure sewer system, we're not installing the pipe down the middle of the road, so you don't have to shut down the whole road. The pipe can be installed either on the shoulder, but still within the right of way, or if it is in the road, it can be off to the side of the road. So you can still have a lane of traffic open, or even maybe 2 thinner lanes of traffic open. So you're not disrupting the traffic flow and you're not disrupting the community. A lot less restoration with these methods versus with the conventional methods with conventional gravity sewer. So those are the first 2 components of our triple bottom line, the social cost and the environmental cost. And that is the subjective analysis. And again, because it is subjective, it tends to have less of an impact in the decision-making process. It's always going to come down to, when we're doing an evaluation, what makes the most economic sense. So then we look at the monetary component of our selection matrix, focusing on the capital cost and the O&M cost. When we look at the economic cost of our triple bottom line, which I don't know if I mentioned this earlier, but that's also called sustainability. So you might hear the term triple bottom line or sustainability, but it's basically the same thing, looking at social, economic, and environmental. So turning our attention to the economic cost, a few things we want to look at: that initial cost. That's the capital construction cost, both for the public components, the stuff that is in the public right away, as well as the on-property components. Then you have your project cost. These may not vary much, and this is something that is defined by each project, but generally that's going to be the cost of construction observation, the cost of administrating the project, the cost to close out the project and commission it. And those costs can vary somewhat between a gravity sewer system and a pressure sewer system. You're not going to have a lot of variance. Where you might see the variance is if you can install more feet per day of a pressure sewer system compared to a gravity sewer system, your construction timeline is going to be shorter. Therefore, your construction administration cost, your observation cost, and all of that would be reduced. Once we get through that initial cost or capital cost or project cost, then we want to make sure we consider those recurrent costs. And there are 2 components to the recurrent cost. I'm looking at this, and I should have flipped this, but the first one is your operation and maintenance. This is the annual cost you're going to have every year to operate and maintain the system. Then another recurrent cost you would have would be the repair and the replacement cost, or R&R cost. So combining this, you will sometimes see this reported as OM, R&R. And the repair and replacement cost is a recurrent cost, but it's not necessarily done annually. So it might be something that is done in year 10, in year 15, in year 20, depending on what the system is. So you want to kind of look at what are my repair and replacement costs and how should I handle them when I do the evaluation. So when we look at our cost, it's always nice to look at it, if not required, to look at it from a life cycle cost analysis. Now, life cycle cost analysis is a process that evaluates all the current and the future costs necessary to construct, operate, and maintain a sewer system. So with the life cycle costs, we're looking at both the capital expenditures as well as the operation expenditures. Again, these are what I hit on earlier, where you have the engineering, construction, project administration are your capital costs. Those are generally going to be reported in current year dollars. And then your operation and maintenance, your repair and your replacement, those would be future year dollars. In the case of an operation and maintenance, that will be a cost that you're going to see every year for the next X years. Repair and replacement might be a cost that you see in year 15, or for another piece of equipment, that might be a cost you see in year 20. And again, you want to make sure you understand how you're handling those repair and replacement costs while you're doing the evaluation. The importance of a life cycle cost analysis is that it provides a structured method to provide a standardized assessment of sewer system alternatives. You want to make sure everything is being evaluated on equal footing. You don't want one person doing an evaluation of a pressure sewer system in one office, another person doing an evaluation of a gravity sewer system in a different office, come up with a recommendation, and you find out that their life cycle cost analysis was not done to a standard format. Therefore, it's not really a comparable evaluation. Certainly on its own, the results may be correct or acceptable, but when you look at it through a comparative lens, when you're looking at it in terms of making the selection of an alternative evaluation, you want to make sure that the process is consistent and repeatable. And the key thing is, it really provides the decision makers with all the information needed to make that responsible decision. At the end of the day, someone has to decide that we're going forward with a pressure sewer system, or it happens, we're going forward with a gravity sewer system. They want to make sure that they had everything necessary to make that decision and that they can defend it to the ratepayers. Life cycle cost analysis is evaluated in a present worth process. So it converts all costs to a present value. And these costs, again, this is just kind of repeating whatever we said, but that's your initial capital construction cost, your initial project cost, your operation and maintenance cost, and your future repair and replacement cost. And you use standard economic formulas to do this evaluation. The graphic I have on the right-hand side of here, those are just standard formulas that take future value in the top formula, future value, using the discount rate and the project evaluation period, which is N, and brings it back to a present value. And then this formula below that, the PV equals A formula, that takes all those annuity cost. A is the annual cost. Again, uses the discount rate and the N being the project evaluation time period, and brings all those future annual costs to a present value. So you want to bring everything forward to the present value. When you're doing this, looking at the formula on the left-hand side of this slide, the LCC equals PV plus, you can see that a lot of the current year dollars would already be in present value. So when we're doing the evaluation, we're saying, okay, here's the construction cost. We're going to do the construction cost in present year values. But we want to make sure that we bring all the future costs, the operation and maintenance, the repair and replacement costs forward. And we use what is known as the uniform series present worth formula to do that. And again, that just brings everything forward. So you have your I, which is your discount rate, which is the economic factor, the interest or inflation, not inflation, but the discount rate, the cost of money. And then N, which is the number of periods you're evaluating. So you look at those costs that occur year one all the way up to year N and bring those forward into present year value. Now, I was saying earlier how you handle the repair and replacement. You could say that on this, you have a cost of replacing a component in year 5, year 10, year 15. And you can look at it in year 5, year 15, year 10, year 15, and bring it forward. What I like to do is treat it as an annual cost. So I know if I have to replace something in year 5, I would take that number, divide it by 5, and then say, okay, so every year for the next 5 years, every year for the next 20 years, I'm going to put this much money aside so that I have that replacement cost when it becomes due. It makes the process just a little bit easier, and it really doesn't change the bottom line number. Because what's important to remember too is this is a top level evaluation. So you're looking at a lot of unknowns. You know, there's guidance on what the discount rate is. We're guessing on what things are going to cost in 5 years. So, you know, it's an evaluation. So if you look at something that just applying it a future cost in year 5 and bringing it forward versus distributing that over 5 years and bringing it forward, it's not going to change the overall number much. And it's certainly not going to change the evaluation process at all. So when we want to do the present worth analysis of the life cycle cost, first things you want to go through is make sure you understand the system and establish the system parameters. So we want to look at that initial construction cost, including the project cost. You also want to look at the operation, maintenance, repair, and replacement costs. You want to make sure you capture everything. So you want to look at what are those activities, what is the frequency in which that activity occurs, and what are the costs associated with that activity. You might be, you know, an iterative process where you say, okay, I definitely got to do this and this. So let me include that. And then as you work through the process and you start that thinking, and that's one of the things, one of the benefits of doing a life cycle cost analysis, particularly a structured cost model, is it kind of forces you to think and say, oh, wait, did I remember this? Should I include this? How do I handle that repair, that pump replacement in year 20? So you want to make sure you capture everything and then figure out how to handle it. You also want to make sure that when you're doing the collection system evaluation, that you account for the projected wastewater flows. You all will recall from part 1 and part 2, where a key difference between gravity sewer systems and pressure sewer systems is infiltration and inflow, where you have that wastewater that is the base wastewater flow. But in addition to that, with the gravity sewer system, you would have groundwater and stormwater that enters the system through deficiencies in the gravity sewer system. You don't have that infiltration and inflow problem with pressure sewer systems. And why you need to consider that is there is a cost associated with infiltration and inflow. It costs money to transport wastewater and to treat wastewater. So if you have clean groundwater entering your sewer system, your gravity sewer system through a deficiency in the pipe, you got to pump that to the wastewater treatment plant. Once it gets to the wastewater treatment plant, you got to treat that. So there is a cost associated with that. So this is one area. Not only do you need to consider the initial capital construction cost, the OMR&R cost, but when you're looking at a sewer evaluation, you want to make sure that you capture some of the other costs that might be unique to that application, such as the infiltration and inflow. Then you want to establish your financial parameters. So you get your cost escalation rate, if you're accounting for inflation, or your discount rate. And depending on your discount rate, you don't necessarily have to account for inflation. So I'm not going to go over in any details what the discount rate is, what the cost escalation rate is. That's the number when you're doing the electrical cost analysis. You can get those numbers. The number I always use comes from the federal government's Office of Management and Budget, OMB. Yeah, OMB. Depending on where you might be working on a project, state guidance might tell you where to get that number, that discount rate, or might provide a discount rate that is going to be used. If you have a funding agency, they will probably give you that information. And then you want to look at the project planning period. It's generally going to be somewhere between 10 to 40 years, but you want to make sure you capture all the costs that occur over the time. You don't, if you have too short a period, you're not going to capture all the true operation and maintenance costs. If you have too long a period, you're starting to make guesses on what something's going to cost 50 years from now, and we certainly don't know what that's going to be. So you want something that kind of falls in a nice sweet spot. And again, this is something that might be governed by who's ever lending the money for the project. Funding agencies will usually say, if you're going to bond this project for 20 years, for 30 years, the life cycle cost analysis has to meet that period. You know, if it takes you 30 years to pay back that loan, they want to make sure that you did an evaluation to show that this is the most economical, viable solution going forward. I always like to say there's, 4 cornerstones in my assessment of a life cycle cost analysis when we look at the keys to success. That is a system that is repeatable, that you do it the same way every time, and everyone who does it the same way every time. There's some flexibility, which is the second cornerstone, where you can change some of the factors, but the process itself should be structured and repeatable. You do want it to be flexible though, because everything's not the same throughout the communities that we'll be working in. That leads us to the third cornerstone. You want to be localized. How something is handled in California would be a lot different than how something might be handled up in Toronto or Quebec or in Florida, or we get into Minnesota. It's all going to be different, both in terms of the construction cost, the construction impacts, but also in terms of what the costs are, how we address it. And then most importantly, at least from my perspective, is you want it to be defensible. This was another hard lesson I learned when first time I was doing some evaluations. I thought I had the answer. I go in, I meet with the client, and then all of a sudden, no one told me that the client was going to ask questions, and I would have to defend that number. I certainly was able to do it, but then I found that if I were able to set something up in a structured format that was on a spreadsheet model, I can not only defend it, but I can also address another component of this is, well, what if? So when they're asking you to defend a number, they say, well, yeah, but you have this value, Keith. What if it was that value? If you set things up as a nice little spreadsheet, then you can go in and change those parameters. That leads me up to the segue where the spreadsheet is a nice tool to do a life cycle cost analysis. So Rachel mentioned in the introduction, we have our life cycle cost analysis that a link will be forwarded to you, to the attendees of this. And what our life cycle cost analysis model is a spreadsheet-based model that provides ease of use, consistency, provides structure, flexibility, defensibility, and guidance. And those are really the critical components as we look at a system. It is a planning level tool to provide an assessment of the evaluation for the total cost of ownership for sewer alternatives. So it is the early stages of the evaluation. The results are based on standard system parameters and unit cost, and it's really just intended for comparison purposes only. We're kind of using global numbers to start that process. It can be refined as your information becomes more detailed, but really it's just a top level approach. Going through, first thing we want to do is establish the system parameters, looking at the initial capital construction cost and the project costs. Again, the engineering, project administration, O&M. And when we look at this, it's important to really see the difference between the capital construction cost between gravity sewer and pressure sewer systems. This is a table that we developed looking at a lot of bid tabs, a lot of third-party reports, where we looked at the cost of a pressure sewer system and a gravity sewer system. And these are not necessarily E1 projects. These are things that we've just compiled a database of projects that looked at either bid tabs from projects that were either pressure sewer systems or gravity sewer systems, or third-party evaluations report where they may have evaluated both pressure sewers and gravity sewer systems as well as other alternatives. And we find consistently, and this is based on our experience, we see as well that the typical cost savings a pressure sewer systems can be 35 to 50% cost savings over a gravity sewer system. The construction cost drivers, I touched on all these points, but with gravity sewer systems, you have the larger diameter pipe, deeper excavations, and you're going to have many lift stations. It'll tend to have more extensive restoration with a larger environmental disturbance. And one of the things I would say anecdotally, the biggest component of a change order when you're doing gravity sewer systems is going to be subsurface. It's either going to be the rock that you didn't know was there, and in most cases, potentially higher dewatering cost. With the pressure sewer system, you have smaller diameter pipe with a shallow excavation or horizontal directional drilling, follows the contours of the land. So you have less need to have that constant slope down, that if the terrain changes a little, you can just set 3 feet, 4 feet, whatever it is, and keep that constant depth. That makes the construction go faster. You have few, if any, basin area lift stations. So with the pressure sewer system, with the smaller diameter pipe and the quicker installation, you have smaller equipment, smaller crews, less environmental disturbance costs. That's a big cost savings when you have fewer people working for less time period to install a sewer system. You also have a lot more flexibility in the construction phasing. So you can do just the mainline sewer now and then come back at a later time and do the on-site components. When we look at that, this graphic really illustrates the difference. This is from a lot of third-party reports where they did an evaluation of pressure sewer systems versus gravity sewer systems. I went through, broke it down into the main components of mainline sewer, appurtenances, which are your manholes, your air release valve, your cleanouts, the on-property component, the restoration, the lift station. And this just kind of shows you the breakdown. And what's really interesting here is, as you would expect, with the pressure sewer system, the component of on-property cost is higher. But the advantage of that is if you're installing a pressure sewer system, you can install the mainline sewer first. And based on this data analysis, you can see that for a pressure sewer system, the mainline, the sewer that's in the road, is 23% of the similar cost for a gravity sewer system. So if you're looking at some construction phase-in where you don't have all the project budget now, you can do part of it now, install the mainline sewer now, and then second phase, third phase, subsequent phases of the project, go back and install that on-property component. This again, this is also a big thing if you're looking at a new housing development where the developer only is responsible for installing the mainline sewer. The homeowner, once the house is sold and turned over, they're responsible for perhaps installing the on-property component. So it's important when you're doing that cost analysis, not only look at the high-level cost analysis of gravity versus pressure sewer system, but how is that cost distributed and how does the flexibility in that phase-in impact the economic evaluation? So then the next component, once we get through the capital cost, is establishing the system operation, the equipment maintenance, the equipment repair, and the equipment replacement. And here I have a subtitle there or sub-bullet on short-lived assets or short-lived assets. If you're working on state revolving fund in some communities, you have to account for how you're going to replace any asset that has a life less than 15 years. So you want to make sure you capture that and include it. And again, as I mentioned earlier, you want to go through your operation, maintenance, repair, and replacement and look at all the activities, the frequency, and the cost. What we did with the life cycle cost model is we have some default values in there, some default parameters in there to kind of remind you of, hey, have I considered this? If you did consider it and you don't think it is required, you can zero it out. But it kind of helps to make sure you go through that process of what is my OMR&R? What are those activities? Have I captured everything? It's very important that you want to go through that process. Particularly when you're looking at maintenance. I mentioned earlier, one of the things we'll hear from time to time is people like gravity sewers because once it's installed, it's free. And that is not the case. I once had a conversation on that point, standing next to a $600,000 vac truck. $600,000 vac truck is not the definition of free gravity sewer system. So you have to have that ongoing maintenance. You want to have some proactive maintenance. With the gravity sewer system, you have to TV and clean the system regularly. With a E1 semi-positive displacement pump, there's no real proactive maintenance. You want to keep an eye on it to see, when is it time to maybe replace a stator or is something not quite up there? Should I take a look at that? So there's a little bit of preventive maintenance, not necessarily proactive maintenance. But when we look at the components, you have proactive and preventive maintenance. And you want to make sure you address that so you don't have to spend money on the back end on the reactive and the emergency maintenance. So as I said, with the gravity sewer system, the regular inspection cleaning is necessary. You don't want to have any blockages within the system. Unfortunately, with horizontal assets buried on the ground, we don't see what the problem is. So if a municipality is not regularly inspecting their system, they're going to have some problems, and that problem is going to come through a discharge through a manhole, a basement backup, or a lift station overflow. So you want to maintain that. Usually it's part of a consent order, but here's a table that shows the US EPA provides some guidance where they would recommend that you inspect CCTV 7.8% of the sewer system annually, clean about 30% of your sewer system annually. So you want to have that ongoing inspection and cleaning process of your mainline sewer and your manholes. And the table on the right, which adjusts the cost for current year values, you can see that CCT inspection is about $7,000 per year per mile. So if you don't account for this cost during the evaluation process, you're only looking at the initial capital construction cost. That's a big cost to get hit with later on down the road. When you're looking at cleaning that $2,000 a mile, and if you got to do 20% of your system because you have backups, that is a very big on-plan cost. You also have the gravity lift stations. Those require regular visits, daily, weekly visits, quarterly visits, wet well cleaning. You also have concerns with power, odor control, and chemicals and landscaping at the plant. It's going to vary depending on what size the lift station is, where the lift station is located, but it's definitely an O&M component that has to be accounted for during the process. Now we look at pressure sewer systems O&M. One of the concerns that you might hear is, you got these 200, 300, 500, 1,000 grinder pumps located at each property. Well, these grinder pumps, particularly with the E1 progressive cavity grinder pumps, are more like an appliance. Our DNA comes from a group of engineers who went on to found Environment One, but they were at the time General Electric engineers, and they developed this process with an appliance mindset. So there is no preventive maintenance. The life expectancy of the pump is about 15 to 20 years, in some cases even more, with the mean time between service of these pumps of about 10 years. We also look at the cost of ownership. The electrical is normally borne by the homeowner, and that's generally much less than $25 per year, probably closer to $15, $10 per year. And then when we look at a collection of pumps and we see what is the cost of maintaining those pumps over the life of the system, we find that generally, and we have many case studies that back this up, the annualized pump maintenance cost is about $30 to $50 per year per installed pump. Now, I do want to make sure I'm clear on this, that when there is a pump repair, it does not cost $30 to $50. But if you had a sewer system, pressure sewer system with a large collection of pumps in there, and you put aside $30 to $50 per year for each of those installed pumps, when you do have that service call with the mean time between service of 10 years, you have that reserve fund to pay for those costs. And then on the mainline part, generally we have not seen any mainline pipe for pressure sewer systems, generally insignificant. We have many systems where they will install a cleanout that they can flush if they have to, but generally that component, there is no O&M of the mainline sewer required. Excuse me. So when we look at the life cycle cost comparison calculator, is a tool that was mentioned, is available on our website for free, and it provides the evaluation for various sewer alternatives. It requires very little information, that just based on the number of service connections and the distance between connections, it can provide a quick assessment of what the life cycle cost value is for the sewer system selected. You can select either gravity and E1, or you can add septic tank sewer systems or vacuum sewer systems. And as I mentioned earlier, these values are concept level because it just uses sort of some models parameters. But the key part is it's flexible. There's any parameter used to calculate the system requirements or the cost requirements can be changed by the user. So that means all of these fields that we have a component with a user defined or with a unit cost, that can be changed by the homeowner. By the user. On the operation and maintenance, there are components in there for suggested operation and maintenance with an associated default value cost. Those parameters can be changed. The parameters and the cost can be changed. So there's a lot of flexibility, so we don't have that bias in there. And it provides that standardized approach that eliminates the bias, but is also defensible. And then if you're looking at the O&M, maybe there's a parameter in there that we don't have as a standard. You can add something to it. So when you sit down and you say, okay, what operation and maintenance do I have in this? Well, you want to miss that in there, so let me add that. But again, we want to it's a standardized approach. You can go in, change the values, and get the results that you're looking at. And then when you do that, that completes the third component of the evaluation process of going through what is technically feasible. Now we just can wrap up what is economically feasible, put it all together, and with the results from the life cycle cost analysis cost model, you have something that is defensible. And when you're in there and the owner says, or the client says, well, what if? You also have the flexibility to change those values and address those what ifs.
Okay, Keith, thank you so much. for that excellent presentation. There's so much content, lots to consider. We have about less than 6 minutes before we wrap up. We've had some questions come in. So I'll ask you and Chris Nedwick to be available to answer some. So some of it you covered in some slides previously after the questions came in, but we'll reiterate them here. Are your O&M costs typical of utility cost or contracted maintenance? A lot of systems appear to be owned and operated by homeowners. How much is charged annually by a service provider to do annual maintenance for a homeowner?
That is really going to change or vary depending on where the utility is. Certainly there are many utilities where there's some fees in there that cover everything that a homeowner doesn't have to worry about. I'm going to put Chris on the spot because we were talking, I think a little earlier today, we were talking about some of the O&M costs in some of our projects. Chris, do you have anything in terms of what you might see with the operation and maintenance cost handled?
Yeah, can you hear my audio okay?
Yes, sir.
Thank you. The only thing I'd say, and hello everyone, is that most of our O&M data comes from municipalities because they're the ones that keep the records, right? We don't see that frequently from private end users. So that's why it's very prevalent. But I'd say it's probably 50-50 in terms of, the end user between municipal and private if you looked at the entire installation base. I know you're looking for a budget number, so just to throw a number at it, I have seen costs of about $150 per year for basically an insurance policy. No matter what goes wrong with the pump, it's fixed by the local distributor, but they can also be much lower than that with different terms and conditions. And I hope that's a sufficient answer.
Thank you. Here's the next one. What bedding conditions do you recommend for pressure sewers, particularly against movement, heaving of small rocks under the pipe?
Well, it definitely needs to be bedded. I think we have some guidance on our website where you would have a stone bedding or you certainly want it to be ballast to prevent against that. And those are standard sort of engineering calculations that it is going to depend on what the water table is, what the subsurface conditions are. But yeah, I said you can just see our website where we might have a little bit more guidance, but you definitely want to make sure that you have a nice clean excavation, a nice gravel bed for the pump to sit on, and then the appropriate level of ballasting to keep the tank from the basin from popping out of the ground in a high water condition.
Okay, this next question comes in from Ronald. Does easement acquisition on individual properties become a cost of the project?
It could. Every project's going to be different, and when you're doing the evaluation, I would put that under that project cost that I had in our lifecycle cost model. We have that as a percentage of construction cost. So yeah, it definitely could be a consideration. It's just a matter of how each utility or municipality would want to handle it. I've worked with some engineers doing evaluations with our lifecycle cost model, and they don't want to include any of that project cost in there because the municipality handles that as a different line item. So it is a cost, probably no different than the cost you might have with some service laterals, or if you have to get easements as part of a gravity sewer system. But yeah, definitely something you want to consider throughout the process.
And here's a question regarding what, unfortunately, in this day and age has been very common regarding flushable wipes. Do we have any issues with those?
Flushable wipes, as Rich said, is a common issue. If there are a lot of wipes going into the system, it could create a problem. No different a problem that you would have with those wipes going down to a lift station or getting clogged up in a manhole. What I personally like about the E1 system or the grinder pump is it instills a sense of personal responsibility. If you have a lot of wipes going into the system and it's a gravity sewer system and they clog up the lift station or the treatment plant, you don't know where they came from. If you have a lot of wipes going into the system and they do clog up the grinder pump, you know where the problem is because it's there. But generally, unless it's an obscene amount, they're going to float on top of the water surface. So they can maybe become a problem, but generally they're going to work their way into the system. And again, unless it's a very large non-quantifiable amount, it shouldn't be a problem. But if it is a problem, you know where the problem is.
The only one thing I would add to that is if you're specifying a grinder pump system, the E1 design is the most forgiving when it comes to wipes. It's a prohibited item. They don't belong down the drain. But with the E1 grinder, you are going to have a far more forgiving design than a small centrifugal inlet.
Okay, so look at this. It's 2 o'clock already. We had some other questions come in. We'll be answering those in a follow-up email. So because we're out of time, I just want to say on behalf of all of us at E1, thank you for joining today's session. And we look forward to seeing you on some of our future webinars. We'll definitely be having some coming up in the next month or two. Until then, take good care.